Okay, and this is our mass, and this is our K, and then C, and then we have X pulling it down. Okay, so this is not a forced vibration at all. It is a free vibration, and I'll show you the outcome. Okay, I'll show you the outcome. So the outcome that you will get, okay, I want you all to observe this. Okay, so now the mass that we are going to carry is 100 kilogram. Okay, and then if we change our stiffness, okay, if we change our stiffness to maybe 200, what happened to our system? Can you see? Right? It becomes less oscillating. So if now I want you to observe this, okay? I put a spring of 1,000. Can you see what's happening? So on your y-axis is your what? It's your amplitude. On the x-axis is time. Okay. So if I were to reduce the stiffness of the spring to 200, right? You can see you have less oscillating. Is this true? Anyone have experience with this? How many of you drive a car with very stiff suspension? How many of you, or no need to answer me. So if you sit in a sports car, the stiffness of the spring, is it higher or lower? Any idea? Yeah, higher. So when you sit in a sports car or a performance car, what will happen? You feel every bump. Yes or no? You feel it, right? Because it's designed with high spring stiffness. So the springs that you use are high. So that's why I put in 1,000. You feel every single bump. Okay. Now, what if you don't want to feel any bump? Let's say our springs is fixed at 200. You don't want to feel any bump. You only can change your what? Your damper. So what do? You increase or you decrease? Increase. Okay, so I increase my damper to 150. Okay, can you see it's less bumpy already? Yes or no? Or when your car gets old, the damping coefficient normally automatically increase. Okay. So what we are going to do is we are going to derive a set of expressions to calculate what is the rise time, what is the peak time, what is the percentage overshoot, subsidence ratio, so on and so forth. So we are going to derive all this. Okay, we're going to derive all this. And it's not difficult at all. Okay. Now, as I said in the lecture on Friday, this can be used in what? Your control theory also. Okay, the math is absolutely the what? The same. Okay, the math is absolutely the same. Okay, here we go. So we know that under a system that has a damper, our general solution, or before we go into general solution, okay, let's label this. Now, this graph is very critical. Okay, this graph is very critical. Okay, so the first peak, so I will draw the line. I think I need the graph. When you understand this graph, okay, this graph is the most important. Don't memorize anything, but there are some values down here that you just have to memorize, okay? So this line that I'm going to draw in red, right, is known as your X steady state, okay? And the first peak, the first peak that we have, this is our pi. Okay, this is our pi. And the distance to pi, so if this is our 0 time, okay, that is our 0 time. The first peak to pi, this is known as our what? As our TP. And TP over here, it defines our peak time. Now, I do apologize. The x-axis over here is omega t. Okay, I have a student. He was not upset, but he told me omega t. Okay, so omega t don't mean much. What mean much to all of you is what? Time. Are we clear? Okay, so for now, on the x-axis is omega t, on the y-axis is x. Okay. Now, midway, okay, so that's another line that I'm going to draw. And this line is here. And this is pi over 2. That is pi over 2. And the distance from here to here, that is, or the time from there to there, that is known as our TS. So TS is our rise time. Okay. Now, in all control theory and vibration theory, pi over 2 has been selected as the rise time. There's no reason why. Okay, I repeat again, there's no reason why. You read in any textbook, rise time omega t taken is what? Pi over 2. It's like 0 is here, plus is on the right-hand side, minus is on the what? Left-hand side. Okay, so sometimes studying engineering, we have to be obedient. I was being obedient, okay? You guys know me. I'm never obedient at all. I will break every rules if I can. And over here, this is our 3 pi. Okay, that is our 3 pi. Okay. And then finally, not finally, so we have 2 more lines that I'm going to construct in orange. Okay. So one is too thick and orange, is it? Okay. So this distance over here, okay, that distance over here is our 2% of the amplitude to steady state. Okay. So once what you realize, once the amplitude are within the 2% range of steady state. Okay. So it's about here. So I'm going to have another line. Okay. So once it falls within 2% of the steady state, the distance from here to here, right, is known as our TS. which is our settling time. Okay. Now, how is this? Yes. Okay. Oh, is it? Is it both? Yes. Oh, no, 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 no. Yes. Oh, yeah. You get 1 pint of beer, okay? My apologies. I cannot spell and I cannot recognize the alphabet anymore. Thank you. Okay. Remember before what we did on Excel, right? We put the value equal to 0, we don't get the right answer. But when we put a certain amplitude, the answer is the same, yes or no, right? Because the system will never settle down. If you let the system go on, okay, it will oscillate up and down, up and down, up and down. It never become what? Completely what? 0. That is why we have to have a what? We have to have a range. Are we clear? That is why we have to have a range. Now, for this topic, the most important thing I keep on emphasizing is you have to remember this graph. I repeat again, you have to remember what? This graph. Once you remember this graph, the characteristic of a system, everything is easy. If you don't remember this graph, okay, you're in big trouble, especially things like rise time, peak time, settling time, 2% or steady state whatsoever. Okay, so try to remember this graph. Okay, now, so the expression that we are going to have now, right? We know mathematically this can be expressed as x as a function of time and is equal to e minus alpha t bracket c1 cos omega t plus by c2 sine omega t. And then we are going to have plus x steady state. Okay. So this expression over here is the waveform that you see at the top. Okay. So we are going to find our, so I'm going to call this equation number 1. Looking at our condition over here, if we call this x or time or omega t is equal to 0, x is equal to 0, right? For this case, t is also equal to 0, right? Omega, you bring below to the 0, everything is 0. So when that's the case, what we have is this. Okay, what we have, so we have 0 minus 0, because minus alpha multiplied by 0, c1 cos omega multiplied by 0. I think I have to put the omega together. Plus by c2 sine omega 0 plus xxs. Okay. So from here, we know that c1 is equal to minus xss. Okay. So that we know. So we have found what is our c1 already. Okay. So next, I'm going to define what is the rise time. Okay. So rise time is we specify for TR is the rise time is a performance measure to indicate how fast the system responds. Okay. It is taken at omega t, or is taken at omega tr is equal to pi over 2. Okay. So if you want to find tr, the rise time is equal to what? Pi over what? 2 omega. So this is how we find the rise time. Okay, so I will put down here y pi over 2. It is a known what? Standard. Okay, there's no mathematical reason why, but people decide to use pi over 2. Okay, I'm going to stop here. I'll see you guys tomorrow.